So welcome everybody. This is an annual event, the Carreker Lecture here in the School of Electrical and Computer Engineering. My name, for those of you who don't know me, my name is Steve McLaughlin. I am the chair of the School of Electrical and Computer Engineering. The Carreker Lecture is an annual tradition named after one of our alumni, Jim Carreker. And today we're really fortunate to have Dr. Sivaram from SanDisk come and talk about the changing landscape, I think, that everybody knows about. I'll say a little bit more about SanDisk in just a second. But Dr. Sivaram is the Executive Vice President of Memory Technology for SanDisk, and he's responsible for the ongoing development of the company's industry-leading NAND flash memory, as well as the development of next-generation technologies, including 3D NAND and 3D ReRAM. Dr. Sivaram has over 27 years of experience in semiconductors, 3D memory architectures, process technology, equipment, and materials. He's held executive positions at Intel, at Matrix Semiconductor, and at SanDisk after its acquisition of Matrix. In addition, he's founded and led Twin Creeks Technologies, a solar panel and equipment company, and has served as a board member for a number of startup firms and was entrepreneur in residence at Crosslink Capital and XC Capital. Dr. Sivaram has published numerous technical papers as well as a textbook on chemical vapor deposition and holds several patents. He earned his doctorate and master's degrees in material science from RPI, Rensselaer Polytechnic Institute, and is a distinguished alumnus of the National Institute of Technology in Tiruchi, India. So we're very happy to have you here, Siva. I think one of the things that we continue to learn about SanDisk is their extraordinary commitment to community service, and we heard a little bit about that tonight. And I hope, because many of our students, in addition to their technical careers, community service we know is an increasing interest in SanDisk is doing absolutely remarkable things, and I think we'll have a chance to hear some about that. So thank you for being here, and we're really looking forward to your lecture.
Thank you. Thank you, Steve.
So I'm very happy to be here. My first trip to Atlanta and my first trip to Georgia Tech. There are several of your alumni who are with us in SanDisk. I actually have two of them today with me. It's been a remarkable journey in terms of memories in general and how they are used around the world in all kinds of devices that you use day to day. And I want to take you through this journey a little bit and then take you through, in a more layman's term, what it means to this evolving cloud infrastructure that's happening. Everything that you are doing today in some form or the other is connected to the cloud. How is this whole architecture happening? And with this explosion of data that's around you, what are we going to do about it? Where are the opportunities? What kind of new research opportunities exist? What kind of new entrepreneurial opportunities exist? Where is this frontier moving? So I'll keep it in a relatively even, not very technical fashion, and you can take it later on in our reception or in the question answer to any depth you want me to take it. So I want to spend a few minutes talking about how I'm an officer of SanDisk and a publicly traded company, so I have to say this thing up front. So don't hold me to anything I say. That's what it says. There is a remarkable gentleman I need to start out talking about. I don't know if any of you know who this gentleman here is. So that's Andy Grove. Andy Grove, to many people, is the architect of Silicon Valley. The guy who transformed himself from a pure researcher who did his work in Berkeley about how oxidation of silicon works, to then becoming a world-class administrator at Intel, was CEO of Intel, the guy who put Intel on the map, the guy who revolutionized microprocessors and got it to the place where it is today. I took 2 classes from him. He taught me leadership. to me, he is one of those idols of the industry. The guy, I don't know, there is a saying, he's a Eastern European, classic he escaped communist Soviet takeover of Hungary before he made himself over to the United States. Wrote this book. His famous saying is, only the paranoid survive. Very famous saying, and he led. So I want to make sure I take a minute to acknowledge his major contribution to this whole industry. And there are a few people who worked with him, and these are men in bad clothing. This is the 1970s fashion. The guy on your right is Andy Grove, who just showed the picture. The guy in the middle invented the integrated circuit, Bob Noyce. The guy in the middle would have won the Nobel Prize if he had not died younger than where he is. His compatriot, the fellow inventor, actually won the Nobel Prize for that. And on the guy on the right is Gordon Moore. The Moore's Law, Gordon Moore. Gordon Moore's office used to be around the corner, about 10 cubicles from mine at Intel. I mean, the only difference between my office, I was a new college graduate. I had just graduated from RPI and had gone to Intel. The difference between his office and mine was, to enter his cubicle, you had to go through his secretary's cubicle. That's about the only difference. There was no difference at Intel how he worked and where he used to sit with us at lunch. And so Moore's Law, for those of you who have not heard about it, is sort of the beacon for the entire semiconductor industry. 50 years ago last year, he came up with a fairly prophetic statement that says, every 2 years, 2.5 years, the number of transistors on a chip will double. Simple statement, but you know the power of that exponent. When you keep multiplying something in that exponent, when it goes 2 times, 2 times, 2 times, the size becomes enormous, and it's 50 years old and it's still holding. So Moore's Law, and those three gentlemen probably are the fathers of our industry. And Gordon Moore in particular, all of our continuing revolution in semiconductors and electronics is based on that law. It's more an empirical statement than a physical law that has done. But the reason that is relevant to us is, I want to take it from here to my alma mater. There was another fellow over there that actually, let's see if I can.
And so that led to a proposal for a very simple 4-bit machine. I point out that the 8008 led to the 8080, the 8080, an upgrade was the 8086 and 8088, then the 286 and the 386, and then the Pentiums, and today your PCs are running on what's really a glorified, souped-up 8008, of course, really souped up.
So I'm sorry, the audio didn't quite work out, and his picture didn't come out either. This was supposed to be a gentleman who you've never heard of, a fellow named Ted Hoff. Ted Hoff, whose picture I had on my screen, and we had a minor issue with my computer that it didn't work, so I had to run off of a card, and that didn't quite do it. Ted Hoff was the guy who invented the microprocessor. Ted Hoff was a quiet man in the early days of Intel who invented the microprocessor. And what Ted Hoff was saying was, in 1969, they started on a project called the 4-bit microprocessor 4004, and then an 8-bit microprocessor in 1972 that effectively is still the computer you're using today. That 8-bit microprocessor then became 8088, became 286, 386, Pentium, and whatever else that you're using in a souped-up fashion today is all coming out of that one idea of a simple von Neumann architecture. The von Neumann architecture of computing. I don't know if you guys are a little young to have seen this movie called Trading Places. An Eddie Murphy movie. If you have not seen it, go order it on Netflix and watch it today. Where Eddie Murphy is being taught about commodities. What are commodities? How do I trade? And he is talking about how do I trade in corn futures and pork bellies. Now, the commodity we are all trading in is computing. That computing power is on that idea, simple idea that von Neumann put that up. The von Neumann architecture is all predicated on this simple idea that computing is very hard. Computing is a very, very expensive resource. So you have your program and your data stored in some memory that can be easily altered. You fetch it, bring it to the CPU. The CPU will do all its work, and you get your input-output device out of which you can get it out. Very simple concept. Every computer in the world to this day is organized that way. Right? Intel took that on and made more and more and more faster and faster and faster arithmetic processing units. And now you have a very massive computer functioning on that simple idea still. Unfortunately, the world has changed. And that's what we are going to talk about. Why the von Neumann architecture is now reaching the end of its life. We're going to talk about that. So what has happened effectively is Moore's law said every 2.5 years, you get doubling of the number of transistors. Flash memories have far outpaced Moore's law historically. What we have done in flash memories is, over the last decade, over 50,000x reduction in cost. What this has done to you is enormous increase in amount of information you can store. So when you casually take your cell phone and take a picture and send it or post it on Facebook, and then all your friends go take a look at it and click like on it, it's cost because of this revolution. Right? The revolution is the ability to put more and more and more transistors on that flash chip. Logic, of course, is a lot more difficult. The reason we are able to do this in memory is a much more organized structure. And in this organized structure, we are able to make smaller and smaller devices. Yesterday, we had a party. We introduced a 1 terabyte USB. A little USB card, 1 terabyte. You can have a micro SD card today in any store. A micro SD is about a thumbnail size. 256 gigabyte. 256 gigabyte in a thumbnail size card. When we all started out in our business, the IBM PC-80 used to have 20 megabyte. Now we are talking about getting a 256 gigabyte on a thumbnail, and that is far outpacing Moore's law. Year after year after year. Now we are going into 3D, and I'll talk about 3D in a minute. And so net of it is, it's not going to be too far in the future when you will have a petabyte in your pocket. A petabyte. And I'll even tell you, I don't know, we don't think in terms of petabytes. And I'll even tell you what a petabyte is. And these are all the architectures that we are putting in place to allow for higher and higher amount of storage that is available to you readily. And this availability of storage is absolutely transforming the landscape in multiple big markets. Each of them is close to $1 trillion market that is being enabled by this. Cell phones, $1 trillion market. Computers, $1 trillion marketplace. Cloud connected storage, trillion-dollar marketplace. Consumer electronic devices, another trillion-dollar marketplace. Each one of them is enabled by this rapid growth in our ability to store bits in this really small piece of sliver of silicon. Right? That's the big power of flash, and where we can talk about petabytes in our pockets. So that's what is leading us to this idea of, in 2020, and I'll come back to this point again, 40,000 exabytes of data that's going to be created. 75 billion interconnected devices, Internet of devices, Internet of things. 75 billion of them that are going to be interconnected. 450 million photos updated from your, uploaded from your smartphones every day. I think every hour, 80 hours of video are being uploaded onto YouTube. Every hour. And that is all, as I was saying, enabled by this growth in flash. So just for those of you who keep track of numbers, we now talk in terms of gigabytes. I just told you a terabyte, which is 10 to the 12, or we are just talking about the power of 2, that's 2 to the 40. I was just telling you, you will soon have a petabyte, which is 10 to the 15th bytes in your pockets, soon. We are talking about the universe, in the digital universe. By 2020, we are going to be creating 10 to the 21, 40 zettabytes of data. 40 zettabytes of data. That's 10 to the 2 to the 70. 40 billion terabyte drives of data. In case you are trying to keep track of it, that is 10,000 DVDs for every man, woman, and child in the world. That's the level of information we are creating, and videos, unstructured, unorganized data, that's where most of the action is. Imagine having to process this amount of explosion of data. Now you know why I started with that architecture. That von Neumann architecture, which was so centered on CPU, is drowning in the amount of data that is being produced, making sense out of this amount of data that is being produced. There is a video that is running, and I got to capture that one face. There is a security camera that's running. It needs to match all the people's names, faces, and come back and find that one person in that crowd video. How do I compute? And that's what we are faced with in creating. So data is in layered fashion. If you work from the bottom, the Internet of Things, the things, this is very hardware intensive. Lots and lots and lots of different hardware, everything from your dishwasher to your refrigerator to your Fitbits. How many of you are wearing a Fitbit? How many of you are wearing Fitbits? I see 1, 2. That's, the professors are wearing Fitbits and the kids are not. That's never a good thing. Right? So those are producing information, your watches and your and then they get aggregated into the what we tentatively call the fog. It's not quite the cloud, it's a level below. The fog is where it gets integrated. Mostly it is on your cell phone or in your laptop, or if you have multiple people in a plane, there is data coming over there, or on a computer or a server someplace that's getting aggregated. And then those then go back and forth into the cloud. So the big difference between the cloud and the edge devices, the edge device is very personal. It's your data. Highly proprietary data that has to be secure to you. Whereas the cloud aggregates data, multiple people's data. So if you want to know what your heartbeat is, you get to have your device tell you. After running 5 miles, your heart rate compared to the universe's heart rate, it is sitting up there. So you compare that and bring it back. It makes sense. That's how the structure of the organization is. The natural question is, why? Why can't I have all the data in my edge or have all the data in the cloud? Why do I need to have this hierarchy? And we were talking about this earlier today. The big difference is energy. The farther you need to go get something from someplace, it takes more energy to get the same data. Right? This data is from Chris Rowan over at Cadence, and he normalizes everything compared to one of those FinFET devices. A 16 nanometer FinFET device, if you are just there on chip, on a registry, you're just getting the data right there. He uses that as the, in joules per 64 bytes of information. And you can see the red dot right in the middle is we have to access it outside of your chip, go to the DRAM, get it back. That's what we were talking about in the von Neumann architecture earlier. It is sitting in the memory, you're going there and getting it back. Then you can go to the disk, which is about a little further out in your computer. You're going away from the memory into storage to get it. Or then you can go all the way into the cloud and get it back. Look at, like all engineers, remember this is a log-log plot, right? Log-log plots make sense only to engineers, just remember that, and we like to use this all the time, because otherwise this plot would make no sense to anybody because it will be a mile long on each side. So on one side is 10 to the 6th joules to, look at this, it's 11 orders of magnitude that goes between those two. And that 11 orders of magnitude of energy is the reason you want to keep only a small amount of data in your edge device and you want to go for your large amount of data farther away. Otherwise, if this device will go very large, or if you try everything in the cloud, the battery will be 10 times bigger than the device itself. Make sense? So, given this trifurcation of data, edge device, the fog device, and the cloud device, we'll talk about where the storage hierarchy is. So the second thing that is important is, how do I trade cost of the device with how quickly I can access it? So on this axis, on the bottom is the cost. As you go farther to the right, it is expensive. Farther to the left is cheaper. And on the y-axis, as you go up, it is slow. As you go down, it is fast. So when you put it on chip, you have those yellow things on the other side, DRAM and SRAM. Those are right next to the CPU. So you can access it fast, but they are damn expensive. If you go all the way to the left on top, you have the flash memory that I just talked about, the NAND flash, and then above with it, the hard drive. They are cheap, but very slow. Now we are talking something in nanosecond all the way to the hard drive in millisecond, right? You go from nanosecond to microsecond to, so you have 5-6 orders of magnitude difference in how fast you can get to it. The question is, can I create a universal memory that's in the middle? That's the Goldilocks memory, right? It's neither too expensive nor too slow. So we can make that Goldilocks memory. That's where we're going to talk about in both cases. Can I move NAND to a place where it is fast enough? Or can I create a new memory that is cheaper, non-volatile, and faster? So these are the compromises that we are trying to make today. So when we move that mountain of data, so on top is a model microprocessor. So you have the level 1 cache, the level 2 cache, level 3 cache, and you can see their speeds are in the nanoseconds. The level 3 cache then goes on to the DRAM, which is off chip. You can still get it in the 50 to 100 nanoseconds, very fast. On the other side, you have a hard drive that is in milliseconds. So imagine you are working very fast, you are in Google, you are searching for it, you click on a website. And you go 1001, 1002, 1003, it is not loaded, you click away from it. 5 seconds is all you got. In 5 seconds, if I don't have the website loading in front of you, you will move away from it. Imagine you are Google. Your whole life depends on search, getting you that information quickly. I can't afford that millisecond, multiple millisecond access time. You got to get more and more of it. Unfortunately, you got to use a memory that is a DRAM that is very expensive. Right? So that's why we ended up creating Flash. So Flash is much, much faster, maybe 2 orders of magnitude faster than disk drives. It moves a mountain of data very quickly, and I'll come back to that gap again later, but let's spend a few more minutes on Flash. So what has Flash done for you? I don't know how many of you were born during those days. When you take a picture, you can't see the picture immediately. You got to take it to Walgreens, and Walgreens goes and develops this, and then we'll print it on a piece of paper, and then I'll give it to you later on. Kodak loved it, because they could sell you a film, and they got to sell you the paper to go print it on. Right? In the mid-1990s, 64 megabytes of flash came in on those little compact flash cards. Lo and behold, Kodak went belly up. Right? Kodak, a venerable 120-year-old company, just disappeared. Bankrupt, because they couldn't keep up with the loss of that business. That's what Flash did to the first. Then, how many of you remember, again, many of you have not seen these. These are called floppies. We all used to carry a lot of these around. We used to buy them in big boxes, 4 megabytes per. Right? Of course, went away. A USB stick, I was just telling you, I have in my bag in the hotel a 1 terabyte USB. And then we had VHS tapes. All of us had those camcorders. When my kids were born, of course, promptly used to have those Sony VHS camcorders that used to be heavy enough that you put them on your shoulder and you take pictures. Right? I have a box full of them. I haven't seen them in forever. I don't have a way of playing them anymore. I don't have any way of playing those VHS tapes. Right? 2 gigabyte, you're done. Entire DVD, 2 gigabytes, you're done. Right? And then there was a fine gentleman by name Steve Jobs who decided that, hey, take all of your music, everything that you ever owned, every cassette tape that you owned, every CD you ever owned, and I can give you a little thing called an iPod. And the iPod came in 2004, 2005 and revolutionized everything. And the big deal about the iPod is iPod had flash in it. Right? Now, we don't even think about the iPod because you have one device that does all of this. Everything that we talked about here, that one device does it. You can take your picture, you can listen to your music, you can store your information, everything is sitting in that one. And then of course, that goes with that hard drive, that is all the last mechanical thing in your computer. Imagine, after all these years, there is something that is still spinning. Right? Apple, to their credit, even took away the fan. There's no fan. Fan used to be the one spinning thing in the computer. Right? Spinning things are all gone, and you go with solid-state drives. Right? That is what has happened to every place where there was a mechanical, chemical storage technique. You've now made it into a solid-state flash. So the cost for that utility, it used to be that if you had a coupon, you can go to Walgreens for $5, you can get a 36 exposure developed. Can you imagine for 36 pictures paying $5 and waiting 2 days? So the utility of things gets so much better. Form factors, right? I mean, I am traveling all the way from West Coast to here. My entire plane trip, all I needed was my iPad. I can watch a movie, I can read the news, I can get my email, I can connect everything is done on that form factor is enabled by the fact that there is nothing mechanical. The Surface that Microsoft has introduced, everything is included. It's a full laptop, and again in that form factor. But more impressive is what has gone on in phones. The smartphone, it is unbelievable. Anywhere in the world you walk into, there is a smartphone. And Apple sells you a 16 gigabyte, a 32 gigabyte, and a 128 gigabyte. Each one is separated by $50 to $100. Right? A gigabyte sells for 20 cents, which means that 64 gigabyte, they bought it from us for about $10, and they'll charge you $100 more. That, by the way, is the power of marketing, right? It's not the material itself that. So clearly the flash is not the most expensive thing. The fact that they can get 90% gross margin out of those, even though they buy it from you, they do nothing to it, they just add more memory to it. That is marketing. Anyway, so I hope you guys all don't go there, you actually go to make things. So mobile devices have been revolutionized by flash. It's an interesting thing that I want to show what has happened because of this. In 2005, the entire flash output of SanDisk used to be that little dot that's out there, right? Some of you in the back can't even see it. And that's what has since happened. That's how fast it's been growing. I was just telling Steve this morning that if you put the entire output of our factory, just the wafers that come out, just one on top of the other, it'll be over a mile tall every year. Just the wafers. The wafers are 3/4 of a millimeter thick. We make 600,000 of them every month. 12 million of them in a year. Just go straight up. 12 million at times, 3/4 of a millimeter. That's what you get. Right? The output is just staggering. The demand for flash is staggering, how fast it's growing. The one that I actually want to spend some time actually talking about is that wouldn't have been possible, that level, without this stupendous amount of work that has gone on in assembling. Getting those into usable ways of. So I don't know how well you can see those pictures. 16 of those die stacked one on top of each other in that micro SD card. Or into the phone, 32 of them stacked one on top of the other, so that you can meet that form factor that Apple insists. Apple says, it doesn't matter what you put, you have to put it into that 4 millimeters that it is thick. So 32 die and micro SDs, connecting them one above the other. I mean, each of those wafers are 25 microns thick. 25 micron thick is flexible floppy die. To be able to interconnect each one of them, there is a big packaging effort in Georgia Tech. Multiple groups working on this. This is a huge enabling area for many of these technologies that we are talking about. Right? Packaging as a technology is a revolutionary enabling architecture for many of the devices that we need to make. Imagine if you have to implant a flash device in your heart or putting it under the skin, it's going to be driven by packaging. So the technology is shrinking, and so today in high volume production we do something called 15 nanometer. 15 nanometer devices. On a 15 nanometer device you get 3 bits per cell. 3 bits per cell on a single 15 nanometer device, and I want you to get a scale for this. Imagine that's a 12-inch wafer. On each of those little squares inside is a die that contains 128 gigabit of information. So imagine, take Georgia Tech, draw a circle that goes past Chattanooga, Tennessee, and or Columbus, and just go make a big circle. If you take that 12-inch wafer and expanded it to that size, about 200 miles, then that would be the size of that feature. I just want you to get a feel for how much we compress. If you take that 12-inch wafer and blew it up to the size of the state of Georgia, we are now talking of a minuscule dot. That's that 15 nanometer feature. The trouble is, that's about as small as we can go. At about 15 nanometer, we are now reaching the limit of how small I can print. Imagine if you are a painter. I hope many of you have the ability to paint. If Da Vinci was sitting here painting the Mona Lisa, and he was only given a foot-wide paint roller to paint it with. That's the problem that we have. We are trying to define a 15 nanometer feature. The wavelength of the light that we use is 183 nanometer. 193 nanometer is the wavelength of the light that we use to go print that 15 nanometer feature. So you take a wavelength that is about there to print a feature about there. We have pushed it and plowed it and clawed it to make it there. We have reached the limit of that. We can't take it much farther. That's our problem right now. Right? So how are we handling that? Oh, this is the other one that I just forgot to talk about. This is my pride and joy plot. When I started in this business, we were doing 2-micron devices. And flash, I don't know if you know, how many of you have done your basic devices course, electrical engineering devices course? I see a handful of you. So a transistor is a relatively simple thing, right? A transistor is just a valve. You have signal going from one place to the other, you are regulating it with another signal. And to make it non-volatile, you store some charge. With the stored charge, this valve either stays open or closed. That makes it non-volatile. Very simple device. Flash effectively is about storing some charge that will permanently change the threshold voltage of a device. The threshold voltage of a device says whether it is on or off, and with some charge on it, I can permanently change the threshold voltage. Okay, simple enough idea. So I need charge. Charge is everything to me. When we started out with these devices in the microns, we used to have millions of electrons that were just stored out there to go make that charge. Today on that 15 nanometer device, per state, per 0 or 1, I got 12 electrons. I got 12 electrons. This is the delta change in voltage. Each of those peaks that you see is caused by one misbehaving electron. One electron decided that it doesn't want to stay stored. It decided to jump ship. I get a 40 millivolt change in threshold voltage. Imagine I shrink further and now I don't have any more electrons to work with. That whole device falls apart. So this is the second big problem with NAND where it was. First, I couldn't print it small enough. Second, I don't have enough electrons to work with. So we tried to make these devices that were 3D. So the simple question was, if that silicon real estate was so precious, why do you build California-style ranch homes? Why don't you build skyscrapers? So the idea came to us in the late 90s, and we built these 8-layer devices that we tried to make these cross-point devices. The trouble is, this still does not solve the problem of how small can I make the dimension in the lateral side, right? And then came the aha moment. So what you're seeing is 2 generations of 2D NAND. That rocket-sized things are where you store the charge. Right? It's called actually a rocket device. I think Tuan, who's here, came up with that name. He called it the rocket cell. And in 3D, when you put it out, that's how it looks like. You have these pillars of devices that are standing next to each other. And there are electrons it's stored in that little storage device that's between that green stuff and the red stuff. There's a little oxide, you store some charge in it, or in the poly, you store charge. You know what happens. Electrons are like teenagers. You get them too close. One of them, they're okay. You put a bunch of them near each other, they misbehave. Right? Clearly, night, I have teenagers at home. You get calls from neighbors, calls from buddies, say, can we go do something else? Can we go to the mall? Can we go here? And that's what we call proximity effect. And the proximity effect is the effect of an electron from a neighboring device coming and causing trouble to my device. Right? And as we got them closer, these proximity effects get worse and worse and worse. Soon, the proximity effect is much more than the signal I'm trying to sense. So now I talked about 3 problems with NAND. First is I can't print them. Second is the idea of number of electrons. I don't got enough electrons to go around. The third is the proximity effect. Right? So our partner Toshiba guys came up with a brilliant idea. Why don't I take this, flip them on their side. So now I build the device vertically. So now I have a device that can endlessly go up with all of the rockets sticking sideways. Right? And more interestingly, they put that in a little cylinder. So when you put in a cylinder and all these things sticking out sideways, and you put many such cylinders next to each other, cylinders are very good in focusing the field. There is no leaking field outside, proximity effect goes away. The neighbor to next neighbor, literally, we have built a moat around my house. I've shut the wireless off. The next door teenager can't call my kids. Right? So that effectively removed that proximity effect dramatically low. So I have solved 3 problems in one go. Because I am building vertically, I can make these features very big, fat. So I no longer have to print very small features. Because they are big devices, I can put more electrons in them. I don't have the electron problem. And 3, because that's a nice cylinder, I've reduced the proximity effect. So these devices are just revolutionizing storage. These 3D NAND devices suddenly gave us new life. I can now build 48-layer skyscrapers. Each of those little planes, those green planes that you see, I can build 48 of them, 64 of them, 128 of them. There is no limit to how high I can go. And that is now my new, next time when I come back and say, oh, remember those days when we were talking about a 1 terabyte USB? Now I'll come back and tell you a petabyte USB. That's what's enabling it. Right? Interesting stuff happening here. You can go back and engineer your way out of these major, seemingly unpassable big blocks. Ideas like these come from kids, students, professors thinking together in a free environment such as this. And that's the reason we come and talk to you more often, to tell you what the problems are. Right? All right. So now we have put the flash there. Unfortunately, that gap is still there. Flash has significantly made it better, but now I still have that gap of moving from connected from the CPU to the DRAM to this huge gap before I get to flash. We define it between memory and storage. How much? I got only 2 minutes. 5 minutes. I got till no. Okay, so I'll finish up quickly. Trouble is when you start telling a story, you got to take it to a conclusion, right? All right, in 5 minutes. So a new class of memories is evolving called storage class memories. And storage class memories, this is the Berlin Wall. This is our attempt at breaking down that wall, right? I feel like Ronald Reagan telling Gorbachev, tear down that wall, right? That wall is the wall between the CPU and your access to the memory. And we need to do that with the storage class memories. This is the biggest evolving area there is in this industry. If you're doing research, this is the area to be in, and you got to go back and create new ways of interacting with that memory. And so what this creates is data-centric computer architecture. Particularly useful on the right side, you see how a server that is going to be arranged in a new data center working on the cloud, which is a pooled set of storage class memories that is accessed by a bunch of servers and different nodes. And at the bottom, you have pooled flash, and a pooled JBOD is just a bunch of drives, just a box of drivers, right? And you see this is what HP is now calling the machine, right? Our attempt at it is to create that memory is called 3D resistive RAM. And these are new technologies that are coming up that reduce the latency, very high endurance. So this is a technology that you're going to see a lot more of. You're going to hear a lot more of this technology. And that's what the machine is. If you get a chance, go take a look, read on the internet about the machine that HP is creating, which is the true data-centric architecture. Here, you're moving, instead of just spending time moving data back and forth, the computing resides within the memory. The computing is the pork belly commodity. The data is the king. You sit among the data so you can mine it, you can create these machine learning algorithms, you can create things that are in-memory computing possibilities. And that architecture has to, so from the old von Neumann architecture, you have to get to these. All right, so I have been given the hook. So let me summarize. There is a data explosion, as I talked about. These edge devices are creating an explosion in edge devices. We need to rethink the computing architecture. We need to figure out how to go from traditional way of thinking to data-centric architectures. 3D revolution is happening in NAND flash. This is probably the start of the 3D revolution everywhere else. We are talking about very low latency new memories that will tear down that wall and enable these architectures to happen. And this 3D, this early start that we have made in NAND will spread into every device. It'll probably go to FPGAs, then it'll go into logic. It's going everywhere 3D is going to be the dominant way of thinking going forward. Thank you.
I have a question, but I just want to check to see if there's one question, couple questions, quick questions for Dr. Sivaram.
Go ahead.
Yep.
Thank you for the excellent talk. I really enjoyed it, and I think you used some of the analogies in my classes. That was really excellent. My question is on the importance of 3D technology, particularly such as packaging and interconnection. So everything you showed was based on the wire part. What are your thoughts on through silicon via, and even more, what are your thoughts on the 3D stack and ultimately of not just memory, but memory will cell block?
Yes. So you're right. The pictures I showed were all wire bonded, and through silicon vias are the way of the future, especially for that storage class memory that I just talked about. if you are going to be interacting with the CPU that closely, you have no other choice but to be connected directly. You have to be in such close proximity. The trouble with through silicon vias has always been the cost, and traditional memory designers have been reluctant to waste real estate for quote-unquote packaging. But it is only a matter of mindset change before this becomes a necessity. When you need to have I/O that needs to be communicating at gigabytes per second that across each other, we are going to need very fast, very broad interconnections between devices. We can't make everything monolithic. Right? I wish I could put CPU, storage class memory, and DRAM all on the same device. We don't, we can't. The processes are very different. The only way to connect them going forward that we know right now in 3D is through silicon vias. There are some ideas to do it on edge connections. Same idea, but different implementation. We will have to get there, and you will have more and more of these devices. It's just going through this gestation period. Copper interconnect in traditional logic took 10 years to develop. Through silicon vias now have been 5-6 years in the market. Now we'll start to, it's at the knee of the curve, it will explode.
One
Thank you very much for the inspiring talk. Just like how scaling will stall, we're seeing the end of the horizontal. Stacking will also slow down and eventually stop. You mentioned 128 years. Where do you see that would stop? And what are the factors that will stop stacking years?
Yeah, so this question has been asked of me many times. For every time we think human hubris has stopped us from building higher skyscrapers, Taiwan created Taiwan 101. Then in Dubai, they created Burj Khalifa. They will try to keep pushing the envelope to go up there. So when we ask our researchers how far, they say 1,000 layers. We don't know. We haven't seen a reason why we need to stop yet. The problem in the end is always going to be the same question both of you are asking. I/O will limit it more than the layers. How do I get the information in and out? So people always talk about organic computing. So you can have a DNA and create memory. Within that big a box of DNA, I can store the entire world's information, entire universe's information on that large volume of DNA. The trouble is, it will take the entire life of the universe to go find that information and get it out. That will be the problem when I go up that high. How do I get it in and out?
So thank you very much for a really, absolutely wonderful talk. We have a special memento for your visit here. So for folks that can't see this, this is a special gift we give to special visitors. It's called a crystal buzz. It's a handmade buzz out of crystal, and each one of them is individually made. And this is one where he's holding a USB key.
I saw that.
Thank you so much.
There is that's the cutest thing I've ever seen. Thank you. That's beautiful.
Thank you very much for your time.
Thank you.
And so immediately after, over in Bunger Hinder, just outside to the left, across, we have a reception, including food. And so everybody's welcome to come and speak with Dr. Sivaram and his team, also from SanDisk that are here, and some free food, and that starts right now.
Thank you.